I'm singing. I'm in a store and I'm singing. I'm in a store and I'm singing.
Hey! There's no singing in the North Pole.
The best way to spread mathematical cheer is by solving systems correctly, by learning here. Welcome to another episode of Math and Silly Hats, where we're tackling once again solving systems of linear equations using elimination, this time with hard problems. Hard in that in these types of problems we will have to both rearrange and multiply one or both equations in order to eliminate a variable by adding them together. So we're going to use a little bit of foresight to save ourselves a lot of heartache and time in the long run. The first thing we need to do is to rearrange these. We'd like to get these into an order that is the same in each problem. I like number of x's plus number of y's equals a constant order. That seems like the most visually appealing and closest to the way most of these problems start off. This is called standard form of a linear equation. So let's try to get both of these equations into x's, y's, numbers order. In our first equation, we have x's on the left, good, but then we have this constant we're going to have to move to the right, and we have a y on the right, we need to move to the left. So let's deal with that first equation. We had 4x plus 2 equal to y plus 12. Again, I would like to move the y's to the left side of the equation and the numbers to the right side of the equation. These are all positive terms, so to move them, I'm going to be using the opposite of addition, subtraction. I need to move the numbers to the right side, so let's subtract 2 from both sides. I need to move the y's to the left side of the equation, so let's subtract y from both sides. Now on the right, these two terms are like in that they're both constants, so 12 and negative 2 can combine to be 10. On the left, these are unlike terms. X's and y's don't combine, so I'll simply be left with my positive 4x minus the y I subtracted. And now it looks like number of x's, number of y's, number. Number of x's, number of y's, number. If it helps you, you can put a 1 in front of this y to remind yourself that has an invisible coefficient of 1, or in this case, negative 1 y's. Let's deal with our second equation now. So again, we have x's on the correct side, but y's are on both sides. We're going to have to move all the y's to the left. And then we've got this constant on the left side. It's going to have to move over to the right to get all the constants over here by themselves. So let's deal with our second equation now. So 3 plus 2x minus y equals 11 plus y. I need to move this positive term, so I'm going to be using subtraction on this positive 3 to get all the numbers on the right. I would like all my constants on the right side, so we'll subtract 3 from both sides. X is fine here, y is fine here, but this y needs to move to the left side, so we have all the y's on the left-hand side. This term is positive, so again, I'm going to subtract y from both sides to get all the y's on the left side. Over here, I've canceled my 3's. I have 2x. Negative y minus another y will be negative 2y's. And on the right, 11 minus 3 will leave me with 8. So now we have our first and second equation in the form number of x's, number of y's, and the constants on the right. So now we're ready to multiply, if we need to, in order to eliminate a variable when we add. So here I've rewritten my new forms of my first and second equation that are in the correct order. So the x's and y's and numbers all align. Now if I were to skip my multiply step and go straight to adding, you'd see that I'd end up with 6 x's and negative 3 y's, not eliminating a variable. So we do need to do step 2. We're going to have to multiply one or both of these equations by a number in order to have opposite coefficients. We want either 4x and negative 4x, or 2y and negative 2y. So we can perform the same operation to both sides of one of these equations in order to get opposite coefficients. I'd like to work with my x's here, just as it's the first number I see, and I know that if I multiply 2x by negative 2, I'll end up with negative 4x, and I'll be able to add and eliminate. So let's multiply everything by negative 2. Negative 2 times 2x will be negative 4x. Negative 2 times negative 2y will be positive 4y. And negative 2 times 8 will be negative 16. So now I've yet again transformed my second equation so that it's aligned with my first equation and has opposite coefficients. So I don't actually need this line anymore, since I now have a form of my first equation, 4x minus y equals 10, and a form of my second equation that have opposite coefficients and are aligned. So now that when I do step 3 and I add these two equations together, so I'm going to add this equation and this equation together. We're just going to go by term. 4x minus 4x will eliminate that variable because 4x and negative 4x make 0. 4y and negative 1y make 3y, and negative 16 and positive 10 make negative 6. So we've eliminated our x's. Now we can solve for the remaining variable y. 3 is multiplying y because coefficients multiply their variables. So to cancel that multiplication, I'm going to use division. Let's divide each side by 3. Be left with 3 on the left. Negative 6 divided by 3 is negative 2 on the right. So we believe we've solved for the first variable of our system, y equals negative 2. Now our last step is to substitute this value into either equation and to solve for the remaining variable. I've cleaned up and I'm working with my original two equations because I don't want any compounding errors. So I'd like to solve for x now that I know the value of y, presumably. Because this first equation already has a positive x on the left and is simple compared to our second equation, I'll be using this first equation to solve for x. So I'm going to rewrite this equation. 4x plus 2 equals y plus 12. We believe the value of y to be negative 2. So let's simplify and solve for x. On the left, 4x plus 2 equals negative 2 plus 12 will be 10. I'd like to get x by itself so it's isolated and we've solved for it, so I'll need to use the opposite operation of addition here. I'll be using subtraction to move all my constants to the right so that I have x by itself. Subtract 2 from both sides. We have on the left 4x, on the right 10 minus 2 is 8. And finally, I would like to know the value of x. It's being multiplied by its coefficient because coefficients multiply their variables. Using the opposite operation, division, we'll divide each side by 4 to remove this coefficient from x. On the left, we have x. On the right, 8 divided by 4 will give us simply 2. So we believe we found the value of x to be positive 2. Let's substitute these into our original equations and check our work. To check my work, I'm going to be substituting our values we found into our original two equations and ensuring that we get a true statement, such as 4 equals 4. So I'm going to rewrite my first equation. 4x plus 2 equals y plus 12. And substitute the values of 2 for x and negative 2 for y. And we're going to make sure this is a true statement. So 4 times 2 is 8 plus 2. Is that equal to negative 2 plus 12 is 10? Yes, indeed, 10 is equal to 10. So we know this works for our first equation. Check our second equation. 3 plus 2x minus y equals 11 plus y. Substituting the value of x to be 2 and the value of y occurring on both sides to be negative 2. Negative 2, negative 2. 2 times 2 is 4. 3 plus 4. Negative of a negative 2 is a positive 2. Is that equal to 11 plus a negative 2 is 9. 3 plus 4 is 7, plus 2 is 9. 9 is equal to 9, so we know that we've found the solution to our system of equations. I hope this has helped you become more comfortable with solving systems of equations with elimination. And now that you've mastered both of the difficult methods of solving systems, we're ready for our secret method of solving systems of equations. Join us next time when we graph systems of equations to find their solution. Have a great day, everybody. Bye-bye!
The best way to spread Christmas cheer is singing loud for all to hear.